What's the measure of angle O? Aryan? 33 degrees. That one should be the first one you do. Like on the test, just get those out of the way. All right? There might be several angles that you have to find. Just get those out of the way. Because, I know it doesn't say it, but on the test it'll say these two are similar. We're just going to assume they're similar because that's the only way to do any of them. But if these two shapes are similar, that means angle R and angle O are congruent. It also means angle C and angle W are congruent. It also means angle A and angle G are congruent. So we actually know all the angles in both of those. We just put them on the other side. All right. The next thing I do, I'm missing a side. If you're ever missing a side, we need a scale factor. I don't know why I put side. We should put scale. What is the scale factor of this one? And if you could, give me your first fraction, and then give me if you reduced it or not. Sam? 27 over 36. Does that reduce?
Yep.
3 over 4. And the reason why I gave you the 27 over 36 is because I want to know where it came from. Well, that 27 came from this shape here. And the reason why I want to know where it came from is because this needs to be the top of all our fractions. All right, knowing that needs to be the top and knowing I need to find RA, we're going to say, well, RA corresponds to OG. Well, OG has a length. That is 42. So I'll be 42 over RA equals our scale factor of 3 over 4. Which will be 3. Remember, we are using our means extremes to multiply our means and our extremes. So we're going to have 3RA is going to equal 168. 168 divided by 3RA is going to equal 56. And we have the length 56. All right, questions on the bell work? You have to be able to do these kind of questions quickly. All right, because there's going to be a bunch of them on the test and they get harder, right? So if you see this on a test, this should be one that goes really, really quick. If it's taking you a long time to do these problems, you need to practice. Otherwise, you're not going to have time to take the test. All right, don't overthink it. Just go angles first, scale factor, use the scale factor from there. All right, questions from the homework. Denise, number 2. On the front. Yep, I got you. Well, we don't know any sides, do we? It didn't give us any sides. So the only postulate or theorem I could possibly use would be the angle postulate, which just says if two angles are congruent in either of the two triangles, then they're both similar. So maybe the first thing you need to do is actually find that missing angle in each of these. Well, if I find the missing angle in each of these, for A, B, C, we'd have 60 degrees. For this angle T, that's 40 degrees. And then I'm just going to see if two of those angles match up between the two triangles. Well, we have 60 and 60, so that's 1. We also have 80 and 80. That's our second one. So that falls into our angle postulate. As long as two angles are congruent, it automatically means that third angle. So if you prove all three of them, you can just call it the angle postulate if you want to. Because you can actually show all three of them are congruent in this one. You can actually go that extra step. Cam.
Remember one I checked?
Oh, okay.
I did it, then I checked the answer key, so I got B, C.
Does that make sense, though? I thought you had a question on this one. Okay.
So remember when I got B, C, A is similar to B, C, D, then I checked and it said A, B, C. So is B, C, A.
Say yours.
Remember when I got B, C, A is similar to E, C, D.
Is E, C, D. Yes, that'll be fine.
So it could also be like A, B, C.
Well, there's multiple different ways to write it. It all depends on what the first triangle you write down is. So why ours are going to be different is because I did BAC instead of BCA.
But doesn't it have to be in order from like small to big?
No.
Oh.
You can. If it makes it easier for you to write it, you can absolutely do that. Your first triangle, you can write whatever you want. You could write CAB if you wanted to. It's that second triangle you got to really take the time on. But if it speeds things up, like if you have a normal pattern where you're like, okay, I'm going to go from small to big every single time, it can make writing these faster because you already know how you have it set up.
So as long as you get like the theorem, like side angle, side.
Yep. As long as you have your side angle side, whatever you pick for your first triangle has to match the second triangle. All right, but it is nice to, because you have like a pattern, right? You always do kind of small to big. If you do that all the time, then you can do these pretty quickly. Versus someone that just randomly picks the first triangle and then tries to match it up with the second one. All right, other questions? Hands up.
So 7, 9, and 10, like my similarity statements did not match up with yours. Because I got like, for the number 7, I got like ABC is similar to RTI.
Oh, the actual name of the two triangles that are similar?
Yeah.
Okay, let's look at number 7 real quick. So these you may have to actually... so let's do number 7. So one way is to actually use the numbers or draw the pictures. All right, if I was on the test, I'd probably draw pictures on this one. But if I'm looking at A, B, C, and you come in with similarity, you're making sure they're similar first, right?
Yeah.
So to make sure they're similar, I'm going to go ahead and I'm going to circle the small ones. So I'd circle 6, and I'd circle 9. I'll put a square on the medium-sized one, so that's 8 and 12. And then I'll put a star around this one and a star around that one. Okay, yeah. So we're good at checking it, right? Because we do something like 6 over 9 equals 8 over 12 equals 10 over 15. And that ends up checking out, right? All right, so now we just have to make a statement. So my statement was ABC equals or similar to TRI. What did you have?
ABC is similar to RTI.
Equals RTI. Well, I could just tell. So if I have triangle ABC, right, without even drawing it, I know it has to be TRI. And why I know that for a fact. So let me write it first. And it would match if I drew it as well. A to B is our small side 6.
Yeah.
So that means I have to use the small side first, which is T to R.
Yeah, I see it.
Okay, so sometimes it's nice having these little pictures with squares, and it just can help you visualize what's happening.
Yeah.
Some people are really good at noticing small and big. Other people need little pictures. I like pictures. I'm a picture person in this kind of respect.
But we can also go over
Sure. Did you come up with they're similar?
Yeah, I had that they were similar. I just had
Okay.
trouble with the similarities.
Oh, the similarity statement. Okay, so let's do the same thing where we circle and square. So I'll pick the smaller one out and I'll circle it. Square around 8, and 10 is my bigger side. On this one, my small one is 15. My medium one is 20. And my big one is 25. So if I already picked my triangle, let's say I pick my triangle ABC, is similar to triangle. Well, A to B is small, which means I either need to have T to I or I to T, right? Because that has to be my first one. What's going to tell me what direction to do is, so A, B, B to C is my medium one. I have to go from the small one to TR. So that means I have to go I, T to go T to R. So it should be ITR. Does that kind of make sense?
Yeah. Yeah. Yeah, I think I messed up.
Okay. Other questions from, yeah, Ryan.
So for 10,
Yep.
the scale factor you said was 4 over 5.
Yep.
So if I put down 2 over 2.5, would that be wrong? Or?
Do they all equal 2 over 2.5?
Yeah.
Okay, then you're fine.
Okay.
What I usually do if there's decimals, because we'd have something like, well, that'd be like 8 over, no, it'd be 6 over 7.5. What I would do is I'd multiply the top and bottom to get rid of that decimal. That's just how I would do it. But you can have decimals. I mean, it can be, as long as they're all the same, you're good. Other questions? Questions going once? Twice? Okay, then let's go over to today's lesson. Today's lesson has a major theme to it. Your lines have to be parallel. Your lines have to be parallel to use anything that we're doing today. If you do not have parallel lines, don't use these proportions and go back to similar triangles. I'm going to say that one more time. In order to use any of the proportions from today, you have to have parallel lines. Why do you think I am saying that a lot? Because people mess it up all the time, or on the test. They start using these proportions when they can't do it. So I've seen it over and over and over, so I'm stressing it. These are just if you see parallel lines. So the first one we're going to talk about is the triangle proportionality theorem. And that is, if a line is parallel, boom, to one side of a triangle and intersects the other two sides, then it divides the two sides proportionally. What that means is if, let's go ahead and put an if statement. If we have parallel lines, so if QS is parallel to TU, then A divided by B equals C divided by D. That is true. We're not going to prove it. You just have to know that's true. But it has to be parallel first to use it. So don't start using this on every triangle that has a line in it. It is only if they're parallel. All right? The next thing is the converse of the triangle proportionality theorem. It says if a line divides two sides of a triangle proportionally, then the line is parallel to the third side. So it is just the converse of this one. If A over B equals C over D, if A over B equals C over D, then we have parallel lines. Then QS is parallel to TU. Not used a ton, but it is out there. It is a way to prove that two lines are parallel when having a triangle. All right, so those are two things with parallel lines in a triangle. Well, triangles aren't super. I mean, they are special. But this parallel idea applies to things that aren't triangles. And that's where we come up with this proportional parts of a parallel line. It says if three or more parallel lines intersect two transversals, then they cut off the transversals proportionally. Well, this is almost identical to our triangle proportionality theorem because we're cutting segments proportionally. So in this case, if all three of those lines are parallel, which they are, then we'd have like A over B equals C over D. All right, our very last one. It says if three or more parallel lines cut off congruent segments on one, yes?
What did that, like the other, we had like another theorem like this. What did that one do? Just so I can keep this straight. Like we had like another.
That looks just like this one?
Yeah.
Yeah, it's right here.
Oh, that's it.
This is the old one.
Okay.
Yep, I did exactly what, just to keep the two things straight, right? This one says they're proportional. Has nothing to do with equal signs, right? I don't have AO equals B or F equals G at all. I just said if I have three parallel lines, then they cut the segments proportionally. This one says if you have three parallel lines, and if it cuts it in such a way that A equals B, then C would equal D. So that one says if three or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So that is that old one that says, well, if A equals B, then C equals D, or vice versa. Right, that's one you're talking about, I assume.
Yeah.
Yeah. I was way ahead of you on that one.
Yeah.
All right, so that was an old theorem. That's an old one, but I want to put them next to each other so you don't get the two confused. Once again, bottom one says, well, if I have three parallel lines and A equals B, then C equals D. This one is a more general one. Any three parallel lines, cut your segments proportionally, where we have A over B equals C over D. Yes?
So could it also be like E over A equals F over B?
Say that again? E over...
A equals F over B.
I'm not sure. These are the names, these are the points. These are the lengths.
Oh,
So what lengths do you mean? You're probably right. Because we're...
the length of I don't know.
Are we looking at this one?
I don't know, but like,
It does, because these are two different theorems. This one specifically says if A equals B, then C equals D. That's all it says. The proportional ones, there's multiple proportions we could write. So what proportion would you like to, are you thinking it could be?
E over A equals F over
Are you talking E to F, I guess? Let's use the letters A, B, C, and D. I'm just not quite, because A is a point. So A is that point. So we can't say a point. So you said A over E, right? But that's just point A over point E. Were you talking about A? This A?
no, never.
You sure? Okay, because there's multiple proportions we can write, and we'll get to that in just a second. All right, and that's what I wanted to get to here. Just because our theorem just says A over B equals C over D does not mean it's the only proportion we can write with parallel lines. So what we're going to do is we're going to list basically not all of them, because there's tons of them. We can keep changing stuff or a little thing around and make it equal. We're going to talk about the big ones, and these are going to be all the big possible proportions of a triangle. And I'm going to add an addendum onto there with parallel lines. Because as soon as I don't have parallel lines, I can't use any of these, and I have to go back to similar triangles information. I'm going to say that once more, because I don't want to see this all over the test like I did the past few years. If you have parallel lines, this chapter applies. If you don't have parallel lines, forget about this chapter and just use similar triangles. All right, this is just if you see you have two parallel lines, you can use these rules. All right, I just want to... Real quick, these should be R and S on yours, I do believe. I think I just have an old copy that I copied from, right? Those are R and S? Cool. All right, the first thing. I noticed that I have parallel lines. This is the first one you should think of. Yeah?
Could you still do the similar triangles with parallel lines?
You could. Yep.
It's just considered a shortcut.
Yep, it's kind of a shortcut because all these are going to apply based upon similar triangles as well. Yes, you are 100% correct. So if you're just like, I know they're similar, I forgot all the rules on, we can go back and actually figure this stuff out. All right, so the first one, I have two parallel lines. The very first one you should think of, this is the big granddaddy one, and that is A over B equals C over D. Now, kind of an offshoot of this one. If you remember from like our first lesson that we had on means and extremes, I said you were allowed to switch your means and it still stayed balanced. Well, we can do the same. So kind of an offshoot of this one is the fact that we could have A over C equals B over D. That is just switching my means. Now, knowing that's true, you don't have to memorize all these formulas, all right? Just look at what you're pulling from and make sure you're pulling from similar things on the other one. And this is what I mean by that. So look at A over B. I pulled completely out of the left side. which means I need to do C over D, because C kind of corresponds to A, right? The same triangle. And these are kind of the base of the triangle. Now if you look at A over C was grabbing from the left-hand side to the right-hand side. Now we have to do the exact same order on your base. So A over C has to equal B over D. Just make sure you're a pattern and you're using all of your bits of information. Once again, A over B, C over D is the same thing as A over C equals B over D. Yeah, Sam.
Could you have R over S equals A over U? Is that also?
Let's hold on to R over S for just right now. It's a special case. It's a special case, so let's just hold on to that. All right. Another way we could write this, since everything's proportional, I call this the parts to whole. You can do A over J is going to equal C over K. Once again, I'm pulling from the left side, I'm pulling the top half of the triangle, and I'm pulling this whole length, which means I need to go to the other side and pull half the triangle and that same whole length. Yes?
So with any of these, you switch means.
Yes. Yep. So you could do A over C equals J over K. Yep. That's what I said. I'm just listing the major ones. There are a billion offshoots of this. Yeah, hands up.
Proportional, right? If you did A over J equals D over K, right? That would
Say that again. K over J.
No, A over J,
A over J equals
D over K.
D over K. No. But what could we do to make it balance? We could do B over J would then equal your D over K. See how you're pulling the similar parts?
Yeah.
Similar part down here to the big, similar to the big. But like you said, A over J would not be equal to D over K.
Would that be another major one, or is that just?
Another major one. I put that as a major one. Because what Grant said, we can always flip our means and get it that way. All right, now let's talk about that R and that S. And I'm going to put a little asterisk by it because it has kind of a special relationship. So let's do R over S. And here's why R over S have a slight problem. Our theorem says the parallel lines cut the sides proportionally. It doesn't say anything about these two lengths. So R and S fall under the umbrella of similar triangles only. This is just similar triangles. So if I'm doing R over S, that means I'm looking at this small triangle here. So maybe I'll say R over S equals A over J. It has to be part to whole. So R over S equals A over J, which is also going to equal C over K. When you have R over S, you cannot use B or D. You have to use similar triangles. Maybe that should be in your note. That is just specifically similar triangles if I have R and S. Yeah, Hamza.
I don't really understand why R over S relates to like A over J. Like I don't know why do those fit?
Because they are similar triangles. So if you look at this triangle I'm doing in purple, and then the big triangle here, those two are similar triangles. So this is side over side versus the side of the small triangle over the side of the big triangle.
Can you explain that one more time?
Yeah. Let me just erase some information down here so I have room. So this has nothing to do with them really being parallel. It has more to do with, I can redraw these as two separate triangles. A small triangle. Oof, that is terrible. Oh, we are very laggy today. I'll just do it this way. So this is the triangle where we have R, A, and C. See that little top triangle? And then I'm going to also pull out the big triangle, which has a base of S and has a side length of J and K. All right, so we said scale factor-wise, these are similar, and we could prove it because they do have two angles that are congruent. Well, if they're similar, then the scale factor could be something like A over J equals R over S.
Oh, yeah.
I'm just strictly using similar triangles in that one.
Mm-hmm. Yeah.
Okay, so kind of like my scale factor is A over J equals R over S.
And that equals C over K. Okay. Yeah.
Yep.
Yeah.
And I just want to bring this up because this is just similar triangles. So many people try to use R and S with D and B, and you can't use that. As soon as you see R and S, you are immediately dealing with similar triangles, and you have to do the top triangle versus the big triangle. All right, does that all make sense to... Yeah.
So why can't you use B and D?
It's not part of the theorem. The theorem says that the sides are proportional, but it never says anything about these two lengths. So if you're ever using these two lengths, you are no longer using the theorem. You are strictly using similar triangles. That's why I said put a note here saying you're just using similar triangles.
Because it's all about
Yes. Yep. R and S throw everything off, and you have to go back to regular similar triangles. All right, other questions on that? Because that can be confusing. You have to know this. So that R and S1 always works because they're similar triangles. These only work if you have parallel lines. These are really your parallel line theorems. This is similar. Yes? A over J equals C over K. That does come from similar triangles as well. Yep. Yep. That comes from similar triangles as well. It kind of comes from both of them, if you believe it or not. It comes from both of them. So it kind of walks in both worlds, that whatever you have, you can use it on.
So, yeah, so you can do that.
Yep, yep. But these guys in red, you definitely have to have parallel lines to use 100%. Other questions on that? All right, let's go through the first two problems, and then I'll kind of... Actually, let's do the first one and the number 4, and I'm going to let you try the rest on your own. Yeah, we'll see. All right, it says in diagram, QS is parallel to UT, RS equals 4, ST equals 6, and QU equals 9. Well, that's already listed on there. It says, what is the length of RQ? Now, to save me some time, I'm going to call RQ just X. Then I don't have to write RQ over and over and over. All right, so the first thing I'm going to do is I'm going to ask, are there parallel lines? Check. As long as they're parallel lines, we can do that part over the other part equals the part over the other part. So because there are parallel lines, we can do X over 9 equals 4 over 6. Or you could have done X over 4 equals 9 over 6. Or, I'm done doing ors, I'm actually just going to stick with that X over 9 equals 4 over 6. But there are multiple setups for it. All right, then we can use our means extremes to say, well, I'll have X times 6 and I'll have 9 times 4. Well, X times 6 would just be 6X equals 9 times 4 is 36. X just equals 6. All right, then I want to go over number 4 with you guys. Because 4 is an old theorem. This is old. This is old stuff, but it deals with triangles. So it says in the figure, x, y, and xz are midpoints of are mid-segments of triangle RST. Find the measure. What it means by mid-segments. If x, y is a mid-segment of the triangle, that means y is a midpoint, and x is a midpoint. It also means z is a midpoint because it says that xz is also. Here is why that's important. Since all of those are midpoints, look at that line xz. Since xz is a mid-segment, it means xz is parallel to the base, or RT. More importantly, xz is exactly half the length of RT. We have a theorem that says if x and z are midpoints, then that distance is half the length of that parallel side. Right now that parallel side is RT. So we would say something like xz would equal 1/2 of that RT. Well, half of RT would be 13 divided by 2. I'm just going to leave it as 13 divided by 2. Okay, now they're talking about ST. Well, x and y are midpoints. So that means that side xy, I'll put 2 of them on, is parallel to ST. And xy is 7. Does someone want to make a guess at what the length of ST is then? Yeah. 2 times 7, which would be? 14 is correct. Yep. So ST would equal 2 times that xy, which equals 2 times 7, which would equal 14. I'm going to give you about 4 minutes to try the rest of the problem. So that is number 2, number 3, and then that A, B, C, and D on the bottom. I'll give you about 4 minutes, then we'll come together and do it in class and see if you got them right. Let's see what we got for answers. First of all, for number 2, it says determine whether PS is parallel to QR. How would I do that? How would I confirm that PS is parallel to QR? Sam?
You know, so if each side is proportional.
See if each side is proportional. So give me up some fractions or proportions. 90 over 140. I'm gonna.
Oh,
You're not wrong. You are absolutely. That would absolutely work, but would be a little quicker.
9 over
9 over 40. I would actually do the 90 over 50, but you're 100% right that it could be 90 over 140. That proportion holds. I'm just going from the letter of the law of the thing, but you are 100% right. You'd get the right answer. And if I had 90 over 50, what would my second fraction be? 72 over 40. Perfect. 90 over 50 reduces to 9 over 5. 72 over 40 also reduces to 9 over 5. Boom. Those two lines have to be parallel. You get why your method works too, right? And I bet you came up with them being balanced as well, right? All right, awesome. All right, number 3. I don't think it's 16.
32.
Arian?
I got 96 over 5.
96 over 5 would be correct. What is that in decimal form? Did anyone get the decimal version of that? Cece? It's 19.2. It turns out it's 19.2. I'm going to go ahead and put an X in the space from A to B. Well, since we have nothing but parallel lines, we can do something. Remember, there's multiple things. Sam showed us there's multiple ways to do these different problems. I'm doing 16 over X equals 15 over 18. Using our means extremes, we are going to have 15X equals 18 times 16, which is 288. So we're going to have something that's like X equals 288 over 15, which you can reduce or plug in your calculator and say that was 19.2. Yes?
Could we also do it make the
All right, continuing it on. Letter A says B over K equals D over J. Correct. That is over J. So if we look at that, B over K is this bottom half over the whole thing. So it must be the bottom half on the other side, D over J. All right, A over B equals what? Ishan? It'd be C over D. Yeah, perfect. All right, then we have A over K equals M over what? A over K equals M over what? N. And finally, the last one is A over K equals, and I don't want you to say M over N because it was just answered that way. A over K is going to equal what? Someone new. Someone hasn't answered one. Denise. equals C over, I wrote the wrong one, J. Awesome. All right, any questions on anything we covered today?